I welcome you back to the post-lunch session, which will be taken over by Professor Harsha. I request our head, Department of Mathematics, to felicitate Sir with a token of gratitude.
Okay. Oh, this I wasn't expecting at all. Thank you, thank you. Yeah, you should give this after I do the job.
Actually, this is done by public tribes. They make all these gifts and
Purchase and okay, okay.
make them help them out.
Oh, that's very nice. Huh? Okay, thanks. Thanks for this opportunity to give this set of lectures. And I have seen some of you during another NCM program that we did a couple of months ago. And so this time it's a different topic. It's partial differential equations. And it's more dear to me than the one I talked about earlier. So let us start. Okay. Oh, I don't know. I think you have to click on that. Or... Ah, yeah. Ah, okay. Right. So this is the objective of my lectures, and I hope to cover these topics hopefully in a well-balanced manner as we go along in this during this week. So the objective is to comprehend essential ideas. Okay, so we will not be able to cover every topic. Essential ideas in solving first-order partial differential equations and to understand solutions to the wave equation. Okay? So unlike a typical differential equations course which is taught in most part of India, where the emphasis is on solving the differential equations rather than understanding the solutions, so we would like to change that perspective. Okay? We would like to say that there is more to differential equations than just solving and writing down the analytic solutions. As we hope to convince you that it is seldom possible to actually write down the solution to differential equations. So when you have access to no such solution expression, we should be able to say something intelligible about the solution without having to know the exact form of the solution. So that's what we are after, and I hope we all will convince you that this is indeed possible. In the context of first order equations, we will encounter these candidates called characteristic curves, okay? Then transversality conditions, okay? I have highlighted the most important topics that come in this study of first order equations, okay? And then we will also be touching upon this equation, with special equation known as the Burger's equation, okay? For those of you who have not seen what's a Burger's equation, not to worry, we will see it later on. Okay. And in the context of the wave equation, we will encounter this D'Alembert solution. There is a solution technique which was developed by D'Alembert. D'Alembert is the name of a person. And he helped us give an explicit expression for the solution to the wave equation. And that solution technique we will see, followed by something known as the parallelogram identity. Okay, the wave equation satisfies a wonderful property, and it's associated with this parallelogram that we study in school. Okay, and how it comes about to solve the wave equation we will see. Finally, you are also studying this equation known as the heat equation. There is a big contrast between the solutions to the heat equation and the solutions to the wave equation. This wave equation comes with a property known as the finite speed of propagation, as opposed to heat equation which has got a property known as the infinite speed of propagation. For now it's just a bunch of names, okay? I am not making sense what it means by finite speed of propagation. Something is traveling at finite speed, okay? And in the heat equation something is traveling at infinite speed. And we will try to contrast that as we go along, okay? So this is our humble list of objectives for the next 4 lectures and 2 tutorials. We will slightly blind, what it means to be a tutorial and a lecture, okay? Sometimes during the tutorial we may start lecturing, okay? and we will just see how it goes. The main objective is to at least get a glimpse of what these are, okay? And then there is this Duhamel's principle. We will see what it is. Okay? Can we just take the cursor off the top thing? Can we make it go away? You can just try, otherwise it's fine. So we will start with an equation known as the transport equation. And this transport equation does a very good illustration of what first order differential equations are about. They are very simple to know. Just leave it. I think if you keep it must go on its own. No, right? No, it's fine. Okay. Yeah. So, there is this equation known as the transport equation. And for the next 20 minutes, we will just try to understand this transport equation. It looks very simple, okay? And this is the setting of the transport equation. And you see, whenever we are studying partial differential equations, the unknowns are functions. Functions of two or more variables. And the way we have designed these lectures is we will stick to the number of variables equals to 2. Because we will be able to see the essential difficulties or the phenomena in this setting only. We will not try to complicate things with many variables because we may lose track of what is actually happening with the number of variables. So you are looking for a function u, which is a function of two variables, x and y. X runs in R and y runs in R. And you are looking for real valued functions. At least I am a very simple guy. I never study anything which is complex value because I don't understand complex analysis. So I'll just do real valued functions, okay? So, because there's enough structure here, so let's appreciate that. So, you are looking for a function u such that if you take the first order partial derivative with respect to the first variable, and then the first order partial derivative with respect to the second variable, you add them, it should equal to 0. So, you are looking for such a function u. So, this is what we are after. And it turns out that the general solution to this problem, like if you are just after a function which satisfies this particular property, that when you sum these two, oh thanks, that's what I was after, thank you. So if it should satisfy, you see, you can actually plug this and check. If you take a real valued function of one variable, so I'll just write here, f is some function from R to R. Okay, you take any function f which is differentiable. Okay, you can differentiate once, let's say. Now, if I define this function u as f of x minus y, u is a function of two variables you are after. So u of x comma y is just f evaluated at x minus y. Now you can check that this fellow actually solves this equation, because every time you differentiate f, you get f prime evaluated at x minus y, and then you have to do the chain rule. Okay, once you differentiate with respect to x, other time you will differentiate with respect to y, but because there is a minus y here, you will get a negative sign. Okay, so when you differentiate that, you will get f prime evaluated at x minus y times 1 minus f prime evaluated at x minus 1, I'm sorry, plus with a minus 1 here, because that's minus 1. So that will equal sum to 0. So this is what you are after. You can actually pick any function f which you can differentiate at least once, and that fellow will serve as a solution to this problem. Okay? Now, let us make some observations about this. You see, there is no data here, nothing. You are given a differential equation, and we have just convinced ourselves that this is a candidate for a solution, and it turns out that this is the only candidate. You can pick any f and this will solve. One observation that we can make is, if we take this xy plane, and because the input of f is x minus y, okay? If x minus y remains a constant, that f evaluated at that constant is a constant. So if I have got 2 points x, y such that their difference is a constant, then your function u and that function f are taking the same value for all those points which remain at a constant distance. Okay? If x minus y is equal to some constant, then for all those points x and y which differ by the same constant c, your u is giving the same value. But what is this? This is the equation for a line. Y is equal to x plus c, right? So this is the first observation that we make, that when you are given this first order differential equation, its general solution has this wonderful property that you take these lines which are all parallel to each other, they never intersect because they have all got slope 1, okay, with different intercepts depending on the value of c. So you pick any of these blue lines, your u is taking the same value along each of these blue lines. It is taking some value here, it is taking some other value here. The values may be different depending on what capital F is, but once you are sitting on one line, your u is taking a constant value. The first observation we make is, any solution to this first order transport equation here has got this property that you take lines of slope 1 in the xy plane, your solution stays constant along those lines. You pick a line, you know what the constant value of that function solution is. Okay? You don't know yet what is that constant value is, but at this stage we can say that if I am standing here or here, it's the same value for the function. Okay? That's the first key observation about the transport equation. Next, you see, when it comes to differential equations, there is a famous saying that anybody can solve a differential equation but for the data. Okay, you have to precise the data first. And so now, suppose you are given this differential equation, the same differential equation, ux plus uy is equal to 0. And we have convinced ourselves that any u which looks like f of x minus y solves this problem. But if I tell you that, okay, you have to find a function u which satisfies this equation, on top of that, you also prescribe that if I restrict myself to the x-axis, that is when y is equal to 0, my function should be equal to this function, u0 of x. u0 is a function of one variable and it's again real valued function. So, you are given this setting, let me write on that corner so that this is the general setting we are after. So, ux plus uy is equal to 0 and u of x comma 0 is u0 of x, where u0 is some function from r to r. It's just a function of one variable. Okay? So if you are told that you have to find this function u which satisfies the equation and also satisfies this condition, that when I restrict myself to this x-axis, it should be actually given by this given function u0, then the trouble we had with capital F being very generic, any f could have done this job here, that is taken care of, because see this red line here, which is where the data is given, it intersects each of these blue lines only once. Okay, so I know for a fact that if I stand on this line, my solution should be constant all along this line. If I stand here, it should be constant all along this line. You see, this line is intersecting this red line here. So if I have to be constant all along this line, I have to be taking this value, the value at this intersection. Similarly, on the second line, the value comes from here. For the third line, the value comes from here. For the fourth, the value comes from here, and so on and so forth. So, the data where you are assigning, the line where you are assigning, helps you fix that function. Okay? Because a priori we did not know what is that constant value along each of these lines. The best thing we could say is, on any blue line, your solution should be constant. Now we are able to say something more. We are able to say that constant depends on the intersection of these points. So essentially you are saying this. If I am standing at a point xy, I have to simply compute what is u0 at x minus y. Because x minus y is that constant. Okay, that's the constant we decide. I hope this is clear. So we started with a simple looking equation which is known as the transport equation. We will tell you why it is called transport equation later on. And it has this wonderful property that there are a bunch of parallel lines along which the solution has to stay constant. So if I give you an additional information that on the x-axis your function has to take a particular function value, that decides what are those values that along these blue lines the function should be. Okay? Now, an obvious question that arises is there something special about this x-axis which helped us decide the value for each of these blue lines? Is there something special about this line y is equal to 0? Okay, that's where we assign the data. Okay? So this is the question we are asking. Is there something special about that line? See, what do you want for this procedure to work? You want this procedure will work as long as you have got a red line which cuts these blue lines only once. You have to come up with a red curve which will intersect each of these blue lines only once. That is the only thing you are after. So there's nothing special about this line y is equal to 0. You can take any line actually, and you have to avoid one particular line, and we will see to that. Okay? So, every time there is a message in the chat, I think this happens. Okay? So my title goes away. So anyway, so let's take this. So this is again the same equation. We have not changed the equation. We are after the same guy. Ux plus uy is equal to 0. And is there a question by any chance on chat? No? Okay. Okay. So, the only difference between this equation and that equation is that the data where the data is given, it changes. So here, you see, you were told the value of u at every point x comma 0. That means on that x-axis you are told what is u. Here, you are told where the value of u along this line y is equal to 3x. Okay, y is equal to 3x it is told. So from a picture point of view, so here the data is assigned along this line y is equal to 3x. So I have just drawn that picture, just picturesque. You see, the blue lines will not change. The blue lines are decided by your first line in the equation, the equation itself. It tells you that you take these lines y is equal to x plus c, your solution should stay constant along this line. So the blue lines are not dictated by where you assign the data. So this is that line y is equal to 3x, this red line. See, y is equal to 3x will cut each of these blue lines only once. And that is what you are after. If I want to know what is that constant value of u along this line, I have to just look for the intersection of this red line with the blue line. So this is this point. I have to find out what is the value of u naught at this point and assign the same value for every point along that blue line. Same story here, and you can keep going on. I mean, I have got the handicap of not able to draw infinite lines. Any questions? So this is what we are after. Okay. So there is an equation, and we are told that on the lines y is equal to x plus c, your solution should stay constant. And there are these red curves where you can assign the data, and that helps. Okay. So in fact, we will try to solve this thing. So what are we after? We have to find the intersection of y is equal to x plus c, that's a typical blue line, and y is equal to 3x. And that tells you what c should be. Okay? This we go back to our class 12 days where we substitute y is equal to 3x here. Okay? And that tells you that x should be c by 2. Okay? So once you decide what is x, you know what is u at the point x comma 3x. Okay? You are told this thing. So in place of x, I will blindly replace c by 2. And then 3c by 2. We are told that that should look like sine of pi c. Okay? Now, we have just found, we know what is c. c is y minus x. Okay? So, I just substitute here. Because that is the point of intersection for a line with this y is equal to 3x line. This is the value that you have to assign. But you know what is c? it should be y minus x. And you just plug it. And you can actually plug it and see now that if I take y is equal to 3x here, you get sine 2 pi x. Okay, here, y is equal to 3x. That is the data that you are solving. And you can actually differentiate this with respect to x ones, with respect to y ones, and you will see that they sum to 0. That's the nice thing about having y minus x in the input. Okay. So, and we know that any general solution should look like a function evaluated at y minus x. So it better look like this. If we have not done any mistake, it will come out like this. Okay. So, I hope this is clear. So we are just looking for points of intersection and assigning values for the solution along these blue lines. Okay. Now, why this equation is called transport equation? So to justify that name, we have just plotted this. Ignore for a moment what this t is, okay? Because earlier we used to call y as t and we plotted these graphs, and I did not change the graphs, so that's why. So wherever you see t, you think it is y variable. So what is the expression that we found? We found sine of pi times x minus y. This is the expression that we found for the solution to that problem where you are assigning the data at y is equal to 3x. Oh, this time we will learn how to make this go away. And then, so that we need not bother. No? Yeah, maybe. You did something last time. Maybe it was his presence. We will see. So now, you see, here we have just plotted the graphs. Of course, sine has this property of periodicity. So we have deliberately not drawn it as a periodic function. Okay? We have just taken one copy of it and ignore these dashes. Okay? Because we want to show that there is something transported. Okay? If I plot the periodic function, we will not be able to see the transport happen. So that's why. So if I take y is equal to 0 here, okay, sorry, yeah, y is equal to 0 or x is equal to 0, I think, just a moment, yeah, it is y minus x, that's why the sine of pi times y minus x. Okay, now if I take y is equal to 0 here, I'll get minus sine pi x, and that is this graph. Okay, just look at the graph between minus 1 and 1, and that is at the instant y is equal to 0. Okay, now we have plotted at y is equal to 1. You see the same patch has just moved here. From the interval minus 1 to 1, it has moved to 0 to 2. And at later stage, it has moved from the interval 2 to 4, then to 4 to 6 when y is equal to 5, and so on and so forth. So that particular information that you begin with, it is essentially moving. That's why this equation is called transport equation. Okay, so you feed some information and it transports it in the x-axis, and that's why it's called transport equation. Okay. Now, for these things to make sense, you have to just go home and maybe think about it a little bit. It will be fine. If you are not following the pictures, it's not important right now. So we will. Okay. Oh, it went. Oh, thanks. Huh? So this is the story so far, if I'm not going too slow. You see, we started with this simple looking equation, and we could solve that when we assign the data on the line y is equal to 0. That every time the data line we are taking the red line over. And we also solved it when the data was assigned on y is equal to 3x. In fact, it didn't matter what the data was as long as you assigned it. Okay? It was not very important that it was the sine function. You can assign any function here. Okay? So now, let's keep this game on. Okay, now we are taking this problem. It looks almost similar to the y is equal to 3x thing only, but now we are assigning data on this line, y is equal to x line. Okay, so something very bad happens now when you assign data on y is equal to x. Okay, so you are looking for a function, again, which solves the transport equation and which satisfies this condition. Now, whenever you are stuck to y is equal to x line, you should be equal to 1. That is the data you are assigning. The data is assigned here, but you see what's happening? The red line sits on one of these blue lines. The red line is not intersecting with any other fellow. Our methodology of intersecting the blue line with the red line breaks down completely. So, as long as I am sitting here, I can tell you very confidently that the data should be 1. I mean, the solution is 1. But here, I don't know what I should assign, because this red line, unfortunately, is not intersecting the blue line at all. Okay? And this is not the only problem. Actually, as I said, something really bad happens when you assign data on y is equal to x for this equation. And that can be seen here. You see, suppose you are not listened to me talk for the first 8 slides and I show you this equation. Give me a function u, which is a function of 2 variables x and y, such that when I restrict to y is equal to x line, I should be equal to 1. There is an obvious candidate which does this job. Any guesses? Yeah, constant function. I'll just take u to be 1 everywhere on R2. And when I restrict to y is equal to x line, it of course does the job. And constants I can differentiate however I like. I'll keep getting zeros. And I add zeros, I get 0. Okay? So this is one obvious solution. Y is you just take u to be the constant function. Unfortunately, there are many solutions to this problem. You see, I define this function u to be just some constant alpha times x minus y. I just add this 1. Because it has this particular structure, the input is x minus y, it solves the problem. Because any function you take of the input x minus y, it solves the differential equation. Okay? So, and 1 of course is a constant, it solves the differential equation. And you are just taking linear combination, it solves. So this solves the differential equation, and it also solves this data. When I take y is equal to x, this term just goes away and I am left with 1. And I can just play with it, I can take any alpha. And so depending on alpha, I got a new function. And these are different functions, genuinely different functions. So from this very nice setting of having a unique solution to a differential equation, when I assign data on y is equal to 0 or y is equal to 3x, and I blindly took the data on y is equal to x and something broke very badly, and we are getting infinitely many solutions to this problem. Okay? I hope you are able to appreciate that. Okay? So, whoever sets the CSIR papers, they ask this question. they ask this question more often. I have seen them like left and right, they are asking the same question. So now you can answer that. So now, you see, we are essentially playing with I told you, right, for the first 20 minutes we are just solving one equation, the transport equation. Again, the equation has not changed. So that means the blue lines have not changed. Your solution is constant around there. And somebody comes along and tells, okay, you solve this problem now. So far, we were saying, okay, you assign a data on a line. Okay, now I am assigning this data. On uxx, I am taking x squared. We have just seen that when I assign uxx is equal to 1, it doesn't work. Because I can do the trick of alpha times x minus y. Is there any guesses whether we can solve this? I am fine with guesses. Okay, because any learning will happen first by guessing. Okay, feel very confident to guess things. You see, what's the first thing we said? For any candidate to be a solution to this problem, it should be constant along these lines, y is equal to x plus c. So, this second line, it is inconsistent with that fact that it should be constant. Because if there is a function which satisfies this, then it is not constant along the line y is equal to x. When you change x, the value of x squared changes. So this is inconsistent. So we had this wonderful setting of having a unique solution. Then we saw the horrible case of having infinitely many solutions. And the culprit was y is equal to x line. Okay? Now, on the same y is equal to x line, I am imposing a new data x squared, And here we are stumbling upon the case where there are no solutions. There are no possible solutions to this problem. So, this violates this case that y is equal to x, you have to be constant. In fact, on any line y is equal to x plus c, your solution has to be constant. So that violates that. So there are no solutions to this problem. This is the thing. Sometimes I talk before I show the what is coming. Sorry. Okay. So there are no solutions to this problem. So essentially, to summarize what we have done, we have taken one single equation. Now, depending on where the data is assigned, that red line, what the red line is, and what data we have assigned on those red lines, we have landed on three scenarios. There is a unique solution for a given data, which looks like, u naught evaluated y minus x or something like that. Or there are infinitely many solutions. Think of that y is equal to x line and equals to 1 case. Or there are these no solutions. And for those of you who are fond of linear algebra, this almost looks like, the solvability things for Ax equals to b. There also you always fall on this. Okay? You either have a unique solution or infinitely many or no solutions. You will never have, I'll have only finitely many solutions. There are no such things. Okay? Okay. I hope this is clear. This is just playing with the transport equation. Okay? Now, so in essence, there was nothing special about that line y is equal to 0 or y is equal to 3x, which ended up with unique solutions. In fact, you can take any line y is equal to beta x plus c as long as you take beta to be not equal to 1. Because beta equals to 1 is the troublemaker, because your characteristic lines, these blue lines have got the slope 1. If you have got a bunch of lines of slope 1, if you want them to intersect with some other line, you have to make sure that that line does not have slope 1. Okay, this is from our class 12 days, and that's all it is. Okay, so I keep telling, you can do PDEs if you have done calculus course. Just a calculus course is good enough, and an open mind. Okay, that's very important. Yeah, because my colleagues from other areas, they tend to malign. So now, yes, and I want to. If this topic is coming across as simple, that's my goal. Okay, I want you to do simple things. Let us leave the difficult things to the guys who can do difficult. Let us do simple things only. Okay, so it's just this, some little observations. So now comes the game of naming things. Okay, so this, we all have to make sure that we give bunch of examples and then give the names. Okay. Because in some domains, people start with definitions for the first 5 lectures and then they give theorem. We will do the other way around. So now, whatever these blue lines were, we give the name as characteristic curves. Okay, they are not curves anymore here; they are just lines. But these blue lines, which are kind of dictated by the equation, they are called characteristic curves. And this red line, where you assign the data, that's known as the initial curve. Okay, these are just names we are giving. And what is the philosophy? The philosophy is your red line should intersect the blue lines only once. That is the only philosophy. Then you can solve this problem. At least this problem. Okay. So, now, you see, here the coefficient was 1, here the coefficient was 1. And we just convinced ourselves that in order to solve this problem, you have to make sure that you have to pick the red line, which does not have slope 1. Okay, there's nothing special about the straight red line being a straight line. Okay, you can also take curved red curves actually, the curved initial curves, and that I will get to. Okay, before that, let us convince ourselves that there is nothing special about the coefficients being 1 here. If I take any non-zero constants a and b, okay, and I take this particular problem, and here I am taking this initial curve to be y is equal to 0. Okay, so this is known as an initial value problem. Okay, and I want you to not have this thing that initial value means y is equal to 0. No, any curve qualifies as an initial curve. You see, y is equal to 3x was an initial curve, not just y is equal to 0, because we are tend to always, from these ODE courses, no, you have to give data t is equal to 0, t is equal to 0. You can start at any point and start the dynamics. So now, here we are taking y is equal to 0 as the initial curve and we are starting this. And from what we have done so far, you can actually solve this. See here, the lines where your solution was constant were those straight lines with slope 1. Here the slope slightly changes. When you have these constant coefficients, the slope will depend on this thing. In fact, any fellow, okay, which is evaluated at x minus ay upon b, will solve this. You can plug it and see. Okay, so you will be able to see that this candidate solves this data, because when I take y is equal to 0, I get u naught of x. And when I differentiate this with respect to x, I get nothing. When I differentiate with respect to y, I get minus a upon b. And this b is sitting here, so that will cancel. So that you can check. Now, what can you say from here? You can say that, okay, as far as this equation is concerned, this is the line. Y is equal to b upon a times x plus c. These are those blue lines. The slopes are b upon a. Okay? So, it's not like every transport equation is constant along these lines of slope 1. Depending on the coefficients you have got, when they are constant coefficients, the slopes are b upon a here. Okay? So, the game is exactly the same. You write these blue lines of slope b upon a, and then you have to come up with a red curve which will intersect these blue lines only once. That's the only game. Okay? So, this is the unique solution, and we can keep playing this game, but let's try to generalize. We are going one step at a time. We started with coefficients being 1, now we move to non-zero coefficients, any general coefficient a and b. Now, can we throw in coefficients which are coefficients of x and y variables? This is the question we are after. Can we solve this using similar strategy? Okay, can we find these blue curves and the red curve where we assign the data so that we can solve this problem? That's what we are after. Okay, so I hope the question is clear. We are trying to find a function u of x and y variables such that this equation is satisfied. There is no data yet. Okay. Okay. So this is the question. So we just take inspiration from whatever we have done so far for the first super 40 minutes. Sorry. So whatever we have done so far, the goal is to find these blue curves, okay, where the solution will remain constant. Okay, and then find a red curve which will help you assign values for your solution at each of these blue curves. Okay. So whenever you are talking about curves on R2, okay, you can think of them as a parameterized curve. Okay, because you are talking about curves here, so you can pick a variable tau. You are introducing a new variable altogether, and this method has got a name to it. Okay, the blue curves that you find, they have got a name, right? They are called characteristic curves. So this method is known as characteristic method. So in the case of the transport equation that we wrote, the life was simpler because the curves turned out to be straight lines. Okay. Here we have to work a little bit. We don't know a priori, like we cannot guess that, okay, anything, I mean, these are the curves where the solutions are constant. That would be too good. So we are saying that, okay, we are looking for some blue curve. Okay. Now, because we are looking for a curve in R2, we can think of it as some kind of mapping where, in terms of this variable tau, which runs in some interval I, and this tau is taken to x tau, y of tau. That's what we are after. So we are just looking for a curve parameterized by this variable tau. Okay, I is some interval. Now, what are we after? We define this new function, which is a function of the tau variable. See, when we had those blue curves, no, if you stayed on one blue curve and you defined u at every point along the blue curve, we just realized that it has to be constant. That means if I take this function v along those blue curves, it would have been constant function of the tau variable. When I keep varying tau, I will not change. That means if I differentiate v, I should get 0. Okay, so we take the same q here. Okay, so there is some curve. Unfortunately, we don't know what the curve looks like, but we are thinking that, okay, it has got this parameterization. Now, using this parameter tau, we introduce a new function v, which is essentially a copy of u along that curve. What are we asking? We are asking for the curve where u remains constant. So we are going to differentiate this fellow. We will differentiate with respect to tau. Okay? You get v prime tau. Now we do our, chain rule. You have our composition, whatever it's called. You have got u composition x comma y, and x and y are variables of tau variable. Okay? Now you are differentiating with respect to tau. You use chain rule. You differentiate u with respect to the first variable, evaluate at the point, and then you differentiate the first coordinate with respect to tau variable. You do the same thing with respect to the second variable now. Okay? We are just using tools from calculus now. Now, we are after making this guy to be 0. We want to make this guy 0. V prime to be 0. That means this fellow has to vanish. Okay. Now, you please observe here what's happening. The differential of u with respect to x variable evaluated at some point, actually evaluated all along that curve, times this fellow, plus the differential with respect to second variable evaluated along the curve, times this. And look at that equation which we saw. It also has that structure. There is u evaluated at x, the differential with respect to x times some coefficient, differential with respect to y times some other coefficient. This kind of dictates how you have to find that x tau and y tau. Blindly we are going to take this fellow dx by d tau to be a and dy by d tau to be b. Okay? And if we do that, because you are after a function u which solves this equation, and that sum equals to 0, this whole thing becomes equal to 0. Okay? This is predicated on the fact that you can actually find x tau, x of tau, such that dx by d tau is a and dy by d tau is b. Okay? I hope this is clear. So if we are after a parameterization such that the function v, which is essentially the value of u along the curve, is constant as you go along in the tau variable. So now let's take this. This is what we said. Okay? So you look for this function x tau and y tau such that the derivative with respect to tau is a evaluated at x tau y tau, and derivative of y with respect to tau is b evaluated at x tau y tau. Okay? And for those of you who have done a ODE course, this is a familiar setting. You have got this ODE system with a given a and b. A and b are given functions, and you have to just solve this. And now, if you manage to find x tau y tau such that this is satisfied, then you blindly, wherever you had dx by d tau in the earlier expression, you write this down. And because it's a differential equation satisfied at every point in x1, in R2, in particular the differential equation is satisfied also along the curve. So that fellow will be equal to 0, and we win the game. So v prime of tau is 0, so v is constant as long as you stay on the curve. Okay, so I hope this is clear. So in other words, you have actually found those curves, those characteristic curves, x tau, y tau, such that u evaluated along the curve is a constant. Okay, because this is the name that we gave for v. V of tau was u evaluated at x tau, y tau. Okay, so it all boils down to this system of equations, which are dictated by what the coefficients are, a and b. Okay? So don't take my word for it, we will work out some examples to see what is actually happening here. So you consider this ODE system which helped us solve this. So if you assume, see, let us not try to optimize with what is the regularity of a and b and all. Okay? In these lectures, at least, if you want a and b to be something, you just assume it to be that, and so that you are guaranteed that you can actually solve for x and y. And this is an ODE system. You should also assign a data here. You see, so far we are only after this finding these blue curves, and the blue curves are found by solving this ODE system. Now the red curve is in our hands. We have to assign the red curves. Okay, we have to impose an initial datum for each of these things. So that's why if at all there's a drawback to this characteristic method, is the notations. Okay, so we had x and y, which are the independent variables in the problem. We introduced this tau variable, which helped us design these characteristic curves. Now for those red curves where we want to assign the data, we want a parameter for that also. So that, as far as we are talking, it will be psi. Okay, psi is just, it is again sitting in some interval, okay, on the real line, and you have got this parameterization, parameterized curve, gamma. Gamma is the red curve that we are after, where you are told what is the value of u along every point on this red curve. Okay. Then, do we have a red? We have, yes. So we have the red and the black. So it goes as follows. So there is some red curve. This is the parameterized curve, gamma. Okay. Every point here looks like x psi, y of psi, where psi runs in some interval. Now, you fix psi in that interval, that means you are fixing this point along the red curve, and you feed this point, because this is an initial value problem, this ODE system. You have to feed it a point, and then it will tell you that locally you can solve it for x tau and y. So then the theory says, okay, you feed this point, and then you let that ODE system evolve, and you get a curve passing through that point. Okay, my drawing is too bad. So it has to go through that point. Okay, because we don't have a blue pen, just go with it. This is the blue curve that we are after. Blue is there. This is blue. Oh, it's fine. We can all think that it is blue. Yeah. So it's fine. So this is the typical picture of characteristic method. Oh, thank you. Thank you. So I'll make it blue now. Okay. So you have got a point on a red curve, and you feed that as an initial data for this ODE system, and you get x tau and y tau, which is that blue curve. Okay. So that you keep doing. So you pick some other point here, somewhere here, and you pass that ODE system. Okay. So just take my word for it. This ODE system, if you assume a and b are one-time continuously differentiable function, you can always find these curves. We will not try to master ODEs now. Okay, we'll just, any course that you take, no, you have to admit certain things. Okay, like if you don't know, you just trust the guy who is standing here. You just admit and learn the next thing. Because for some reason in India, like if somebody is not good in basics, they don't let them learn advanced things, because they want them to go back and learn the basics, and by then they are 30 and it's game over. Okay? So, you just let them learn the next things. When the candidate realizes that he or she needs to brush up his basics, and that will happen only when they start doing some advanced things. If you cut their legs in the very beginning, then what's the point? Anyway, so at least in my case, we'll just admit that, okay, you can solve this ODE system, you give a point, you can draw these blue lines. They will not go off forever. That's the theory of ODEs. At least you can say that non-trivially there is some little piece of curve which goes through every point along the red line. So that's the theory here. Now, you give those red curves, you pick any point on the red curve, you feed it to this ODE system, you get these blue curves. And the blue curve has this wonderful property that as long as I'm staying on this blue curve, they have got the same value as the value here, because the solution stays constant along each of these blue lines. Okay, it's exactly the same picture as those red lines, the blue lines and all. It's a bit complicated with the curves. Okay. Yeah, this is the picture which I have drawn. So there is some curve, red curve. So you are feeding each of these points to the ODE system and you get a bunch of blue curves. And on this line, your solution that you are after, it's a constant, and that constant value is given by the intersection point. Similarly here, here. So you have got a family of curves. Okay, when Shivaji will teach tomorrow the nonlinear first order differential equations, which is very hard. It's not to discourage, but but he will give names to these things. Okay, these pictures. I hope you remember these pictures and these red curves and blue curves. So this red curve is the initial curve. Okay, and you see there are these two parameters. Tau, when you vary tau, you are evolving along the blue curves. When you are varying tau, you are not varying psi. You are fixed xi. That means when you fix xi, you are sticking to a point here, and then you vary tau, which helps you go along here. So that's why there are these two parameterizations. Tau to move along the blue curve, psi to move along the red curve. Okay, so that's it. So you have got family of curves, and you know how to assign the values. Okay, and the intersection points, they have got a name. They are called the base of the characteristic curves. Okay. Now, if you open any textbook on the first order equations, most books tend to, now you see, this is what we do, and then they give examples. There is a wrong impression given that you can actually solve these ODEs. Okay, this finding these blue curves. And please take it from me, it is not possible to find these exact expressions for x psi tau, y psi tau. You cannot find them. Okay, you just take your input from ODE theory, which said that okay, if your right hand side is a Lipschitz continuous function, you have got a non-trivial interval of existence of a unique solution. By that I mean this curve can be extended a little bit out of the red line. Okay, so we are just banking on that result from ODE theory, which tells you that this picture is meaningful. And those examples are just to illustrate the fact that you can actually solve them by hand. And we should not take it for granted that you can always solve the ODE system. Okay, and this is what I told in the very beginning, unlike what is taught in the courses, it is very hard to solve the differential equations. Okay, so anyway, so now I think I'll do some examples in the next, there are 8 minutes, okay, so I'll do some examples, and don't be bothered with the number 44 slides. We will take it easy. We will do little by little. So this is the setting now. You see, unlike the previous thing where we were giving the curves to be full lines where they were going off to infinity, it may so happen that this red curve is just a simple patch of line or patch of a curve. It turns out that a simple patch will do the job, and we will see. So this is the setting now. There is a curve gamma, okay, which is parameterized by this psi variable, and you are told what is the value of u when you restrict yourself to gamma. It is some g evaluated at psi, okay, and you are supposed to find the function u with constant, and that gamma is the initial curve. So what you do is, once you are given this gamma, this is a strategy. You are told what is A and what is B. Okay? You blindly write down that ODE system. dx by d tau is A, dy by d tau is B. Now, this is a first order system, you have to feed in the points, and those points are coming from this curve gamma. You feed it, and then you get this. This comes from ODE theory, you take it for granted. And once you get that, this is the assignment. U evaluated at x tau psi, y tau psi is U evaluated at x 0 psi, y 0 psi. Because that is the point where it intersects the red curve. And that fellow is g of psi, because that is assigned here. Okay, so that's how you do. I mean, if not anything, you remember that blue lines and the red lines. You are trying to find those intersection points. There, somehow you are finding the intersection points. Here it's the other way around. You start from the red curve and you start evolving the blue curves. Okay. Okay. So now an example. This whole theory. It is quite simple. I mean, when you write down this general theory, it looks daunting. And if you ask me, of all the partial differential equations, the first order equations are the simplest to write, but hardest to understand. Okay, because there are not many derivatives. As you will see when you are studying other equations, there are a bunch of techniques from calculus like integration by parts and all those things. You cannot do that here. There are very few derivatives. You have to do this. Anyway, so let's take this simple looking example where A is X and B is Y. Okay, and this is the curve. Y is equal to 1. So you are just taking the line y is equal to 1 and you are assigning this data. When I am sitting on this line y is equal to 1, I'll get used to this. So there is that axis. This is x-axis, this is y-axis. So what is the curve gamma? That is y is equal to 1. So this is the red line. So we are told that, okay, when I restrict myself to the points along this red line, I pick any generic point here which looks like x comma 1, okay, I have to simply assign the value e to the minus x square at that point. So that is the initial data which is given. That's the initial curve. Now we have to find those blue lines. The blue lines are found by solving this. dx by d tau is a. What is a here? It is x. And dy by d tau is b, and that is y. Okay. Now we know how to solve this. See, there is only one function which, when you differentiate, will give you back the same function, and that's the exponential. Okay, there is no other function, and so we will just solve that. So this is the initial curve. Yeah, as I said, sometimes I just write things even though I know that it is there. So now that's the exponential, but you have to also feed in the points from this red line. You have to, because this is an initial value problem, you have to feed in data. And the generic point here looks like psi comma 1, right? Because when tau is equal to 0, that's the base of the characteristic, it is psi and it is 1. Because the generic point here looks like psi comma 1. Okay, so you just solve this. I believe we have solved it in there. And this ODE system, with the initial data, is known as the characteristic ODE. So we continue this example. We just solved it now. X now looks like psi times e tau, and y looks like e to the tau. You see, one thing we have to observe. The solution to that ODE system, with that fellow as the data, with any point here as the data, the solution is always positive. So the y coordinate is always positive. Somehow this dictates that you cannot solve this problem in the entirety of R2. You can solve it only in a patch of R2 where y is strictly positive. This is already hinting at that. Okay, so we should kind of leave this idea of finding a solution to this problem at every point in R2 rather than. You see, that picture you have to keep in mind, the one which I had drawn earlier. There was the red curve and only in the neighborhood I was drawing this blue curve. So now the red curve is this. We will find a neighborhood in which you can solve this. Okay? So this is kind of hinting at that. We have just solved that ODE system. This is again, it's giving a wrong impression that you can solve the ODEs. Okay? But this is an example. So now you at x tau, y tau, this is the method of characteristics. It has to be equal to the value of u at the base point, and that is u of psi comma 1, and that is e to the minus psi square, which is what we were told. Whenever you are restricted to the line y is equal to 1, u at the point x comma 1 is e to the minus x square. So that is it. Now, you see, there is e to the tau here, but e to the tau is y. So I can replace e to the tau by y, and I can actually write what is psi. Okay. So I get psi, and here I can write this in terms of x and y. I get this expression. Okay. E to the function, this fellow, you can actually check that this fellow will solve that differential equation. And I am the first to admit this example is giving a wrong impression that you can solve the first order equations. It is very hard to do this inversion. You will not be able to write everything in terms of the x and y variables, because this will all mix up. This tau, psi, x and y, they will all mix up, and you may not be able to invert the relation. Okay. So, but anyway, this is one simple example where you can actually invert and write back everything in the x and y variables. And in your free time, you can actually check that this solves the given differential equation and also the data, which is when y is equal to 1, you get e to the minus x square. Okay? Okay, so this is the picture. See? Y is equal to, sorry guys. See, y is equal to, 1 upon psi times x. That is the equation that you get for the curves. Okay, so these are just lines again. Even for this equation, x ux plus y uy, right? Those are the coefficients. The curves turn out to be just straight lines. Okay, and this is the picture here. This is the y is equal to 1 line, this red curve, and you are drawing these lines, and these are the blue lines. See, they are all coming off towards the origin because they all look like y is equal to some constant times x. So, here you cannot assign a value at the origin, because when you are standing on a line, you have to be constant. On a blue line, you have to be constant. So, every blue line is going to an origin. So, you cannot assign a value at the origin. So, you have to avoid that point. So, you can actually solve this equation only for the inputs x comma y, where y is strictly positive. Okay, so, and when it comes to this first order equations, no, it's usually you are happy if you are able to solve for every point in the neighborhood of this red line. That's good enough. You are not looking for a global solution. By global, I mean for every point in R. So I have just listed what are the things here. So y is equal to 1 is the red line, the characteristic curves are these lines with slope 1 upon psi, and this x is equal to 0 is also a characteristic. That's also a blue line. And each of these blue lines intersect red line only once. This is our necessity that it should happen only once. And they intersect at the origin. So essentially for every point x comma y in R2 such that x in R and y is strictly positive, you can solve this differential equation. Okay, you can assign, and this is the thing that we wrote, e to the minus x square upon y square. It solves that problem. Okay, and this makes sense whenever y is strictly positive. X can be anything in R, but y has to be strictly positive. So this is what. So, may I take another 3-4 minutes, if you guys don't mind? Okay, because there is a slight change in the curve we will make, and we will see how it affects. Because you see now, unlike that transport equation, the blue lines were not given to us now. Okay. Now, you see it's the same equation. X ux plus y uy is equal to 0. But we will change the curve. Earlier, the curve was that y is equal to 1 line. Now we take this semicircle. This semicircle we will take. We will see how that will affect the way we solve this problem. See, again, we have to feed in points from here and find those. And hopefully, see, like the transport equation kind of convinced us that when we were changing the red lines, the blue lines did not change. They remained intact because any general solution were constant along y is equal to x. Here it is not obvious because we start from points on red lines and then finding the blue lines. So let us just to convince ourselves of this fact that actually the blue lines does not depend on the red curve that you pick. They will remain the same lines, the straight lines that we are after. So for that, you solve this ODE system, same ODE system, but only the data changes. Earlier x0 psi was psi and y0 psi was 1. Now here it is cos, cosine psi and sine psi. Those are the points on the red curve that you are inputting. So you solve this ODE system and then you get this. You see, again, these are lines. You are fixing psi, y is equal to some constant times x. These are the lines that you have to avoid some point psi where tan goes off to infinity. So you get this. Again, this is a bad example in the sense that you can invert everything back to x and y variables. You get this. So this elementary calculations aside, this is what we are after, these pictures. See, you have got this semicircle, this red curve, and the blue lines that you find coincide with the blue lines that you found when you input points from this red curve here, y is equal to 1. The blue curves will not change. They are characteristic of your equation. They are not depending on the red curves that you pick. Okay? You will get the same blue lines. Okay? And I make the same observations. You can always look it up. I will share these slides. Okay? They are ones, and in this case you can slightly move a little bit. You can also solve for points along the y-axis. No, sorry, the x-axis, except for the origin. Origin is always a troublemaker in this example because each of these lines are coming to intersect there. So you cannot assign any meaningful value. It will be multi-valued and all. Okay. So the same example, I just manipulate a little further. A is x, b is y. Now, I take this line. Y is equal to 3x is the line. See, gamma is equal to psi comma 3 psi. So, earlier we took y is equal to 1 as the line. Next we took that semicircle. Now we are taking this particular parameterized term, which is y is equal to 3x. This is the line. And if you solve it, you blindly solve. You forget the fact that you know all these things. You blindly solve the ODE system, feeding these fellows. The input for x is psi, the input for y is 3 psi, and you solve it. And when you solve it, you get this. X is equal to psi times e tau and y is equal to 3 psi times e tau. And the characteristic curve is just y is equal to 3x. See, what happened here is you started on y is equal to 3x and you are staying on y is equal to 3x. Something bad is happening here. This is exactly similar to that line y is equal to x that we saw. See, because y is equal to 3x is a characteristic curve for this equation. The moral of the story is you should never pick a characteristic curve as an initial curve. If you do that mistake, you will never get out of that curve. You will stay there because you see the ODE system, no, it's uniquely solvable. You are taking an equation for your curve and you are feeding points from the same curve. You will keep getting the same curve. You will not get out of it. And that beautiful picture we had of, having a red curve and all these blue lines going out of it will be gone. If we pick an initial curve which exactly matches with a characteristic curve, that is very bad story. Because that is the scenario which will lead to infinitely many solutions or no solutions. So this we have to avoid. Okay? We will fall back to the initial curve because your ODE system will keep giving you the same curve. Okay? So with this I will end now. Okay? There are some remarks. So the characteristic curves, they do not change when you change the initial curves. They do not change. The blue curves remain intact. Okay? And the two characteristic curves also do not intersect in any neighborhood of this point. To convince yourself of this, suppose, you see, these two guys, no? So these curves are going, suppose they intersect somewhere. Okay? If they were to my claim is they never intersect. If they intersect, there is something bad happening. Because if they intersect, I can feed that point to your ODE system and evolve. And that will contradict the fact that you can solve this ODE system uniquely. because there are two curves which are emanating from the same point. So thanks to the solvability of this ODE thing, which is a very abstract theorem which tells you that you feed any initial condition as long as your right hand side is locally Lipschitz, you can solve it locally uniquely, and that will be violated if these blue curves were to intersect. So we don't want blue curves to intersect because then you have to assign the same values along both the lines, and that will lead to all kinds of trouble. So in fact they never intersect. That is thanks to ODE theory. That's what I have said. Yeah. This is another thing of me repeating what's about to come. And this is, I should have put this in red, okay? We are not able to solve for this x and y explicitly in almost all the cases, okay? We have to be a bit lucky to solve those ODE systems, okay, even though the examples tell you otherwise. Okay, with that I stop here. I did not plan well because I am in slide 26, there are some more slides. Essentially, in tomorrow's lecture come tutorial, I hope to convince you that, you see, there are these red curves and blue curves, right? And drawing pictures is all wonderful, but in most cases you will not be able to draw these things to convince oneself. So there are certain conditions that you can check. These are known as transversality conditions. That essentially tells you that when a curve, gamma, when it can be a red curve, when can it be an initial curve, okay, corresponding to a given coefficients A and B. So that's what we will see. It turns out that condition, it involves computing the Jacobian matrix or something, determinant of some 2 cross 2 matrix, at least in our case, and that for some reason coincides with whatever you get in the inverse function theorem. Okay, so these are all falling in place for a good reason, and that we will try to convince you tomorrow. Hope. For now, I want you to just, I will share the slides up to 26 because I don't want to give away the story for tomorrow. So you can look up these slides, and the material from here is just, I mean, there is no originality in this. I am not claiming any of that. So this is borrowed from Evans's book, okay, which is one of the references. And I also particularly like this book which was written by Nandakumaran and Datti sir, which is called Partial Differential Equations. They have written this wonderfully for the first order things. You are welcome to just try that. Okay? Thank you guys. Thank you. If you have any questions, feel free to ask. Okay.
Well, so we can continue in discussion session. Post-lunch sessions are always a bit challenging to attend for participants, but thanks to Harsha sir, he made it so interesting with his red and blue lines to understand the concepts. So I sincerely extend my thanks on behalf of all the participants. Tea is there outside, and after this we will have discussion session which will be available only offline. For online participants, it will not be transmitted.
If you have anything,
Sir?
the answers.
Good morning. Good afternoon, sir.
There's a question from online. Yes.
Yes. Sir, my name is Shruti.
Yeah, please ask.
Thanks to the presentation, sir. It was a nice presentation. But I have a doubt. Are you able to hear me, sir?
Yes, clearly.
Yeah. The ODE you have discussed, can we name this as functional?
Can we? Could you please repeat the last line?
Functional ODE. Since
Oh.
the coefficient depends, it is functional. Is it
Like you want it to depend on you as well? I am showing it on the slides here. Could you please make it more precise what you mean by functional? You want this to depend on you also?
Since initial function, right, gamma,
Yes, yes.
it is not a one, it is not a one precise initial function. It depends on something like V, right?
Yes.
Okay. So, is this the functional differential equation?
I do not know the terminology of this. I can actually look it up and tell you maybe in the next discussion session what it means, this functional differential equation. But you see, for now, this psi, you have to just think of it as a parameter which is telling you what the curve gamma is. Okay? And you are feeding every possible point from that red curve to build this family of characteristic lines. That is my understanding of it. For functional thing to come in, there must be something else, but I will certainly look it up, okay, what it means. Okay, on a related note, you see here, in the setting that we are after, the coefficients are all just functions of x and y variables here. But you can allow for coefficients to be functions of u also, and that is the context of quasi-linear equations. And there, that may be what you are after, but we will be discussing that tomorrow, where the coefficients are also functions of the u variable, and it gets a bit tricky, okay, when it comes to quasi-linear equations. But it's the same strategy though. You will write this, you will blindly write down the ODE system, you call it characteristic ODEs, and you are able to solve it or not solve it depending on the setting you are in. Okay. As far as your question on functional ODEs, I will have to look it up. I am not familiar with the terminology.
Okay. Okay, sir. Thank you very much, sir.
Yeah, so I mentioned couple of references. One thing that everybody should have on their desk is the book by Evans. Okay. That is a good book, and Amarnath's book is also one of the references here, and these slides are very much motivated by a chapter in this book by Nandakumaran and Datti. It's called Introduction to Partial Differential Equations or just Partial Differential Equations. I don't know. They have got two books, one on ODEs and another one on PDEs. This PDE book is very nice. Especially for this first order equations. Any other question? Okay, thank you guys. So, can you hear me now? Yes. So this right hand sides, no? If the right hand sides are Lipschitz continuous in the second variable, there is no second variable. If they are Lipschitz continuous, then you can actually solve them locally. That's the general theory from ODE, and the name of the theorem is called Cauchy-Lipschitz theorem. Okay, it tells you that you can actually find these blue curves as long as the right hand side is Lipschitz continuous. Okay, so that you can look at.